So I moved it up a little. And I'm going to do a different example, which is a different example because it's a little different. Natural log of x dx, it doesn't really look like f times g. But you can also use this, you can use integration by parts on something like this. And what you'll find as we go through some other techniques of integration in the next couple of weeks, integration by parts is something that you can try if you can't think of anything else to do. So this is an example of an integral where you can't really think of anything else to do, because if you look at your basic table of integrals, okay, we know what the derivative of natural log is, but there's no antiderivative that has a natural log in it. So, like, what are you supposed to exactly do with this? You can try integration by parts. The thing is, here, you don't have a whole lot of choice, right? Because u has to be natural log of x, and then dv is just dx, because that's all there is. You don't want u to be dx. That doesn't make any sense. Okay? So if I just have one function times dx, and I want to try integration by parts just sort of out of sheer frustration, or I don't even know what to do, then it's going to be like this. It turns out in this example and in the example that we're going to do next, this works out really well. Because the derivative, of course, of natural log is 1 over x, so you have that. And the antiderivative of dx is just x, right? So if I plug this into there, I get x natural log of x for my uv minus the integral of v du x times 1 over x dx. Well, those just cancel out, right? And so then if I've got those canceling out, I just have the integral of dx. Often we don't write 1 dx, right? We just write dx. So if I'm integrating the integral of dx, it's just x. And it turns out that that is the answer. What you can do is if you are not sure, you can always check it by taking the derivative, right? If I take the derivative of this, I have to use the product rule. So I have x times the derivative of natural log, which is 1 over x, plus 1 times natural log of x, and then minus 1, right? And so these guys cancel out. You do indeed get natural log of x staying. That's what we were looking for. Okay? So that is one case where you want to do that, where you can just let u be that natural log of x. Another case where this is helpful is inverse trig functions. If you want to integrate an inverse trig function, it's sort of the same problem as natural log of x, because we know what the derivatives are of the inverse trig functions, but we don't know what, none of the integrals give us that back. So I'm going to do inverse sine of x, and also just because at least one of these, I should do at least one of these as a definite integral, I'm going to pick the definite integral, and I'm going to do from 0 to 1/2. Okay? So whenever you see an inverse trig function, this is really like a good way to go, is to try the integration by parts, because it does work. If I do u equals inverse sine of x and dv equals dx, I do have to remember the derivative, right, of inverse sine of x, right? So that is, again, like, you're supposed to remember that. It's on the chart, but it is 1 minus x squared, square root of 1 minus x squared, dx. So that is supposed to be something that you know. And then here, v is just x, right? So now what do I have? I've got x inverse sine of x. Now I've integrated this, so I can go ahead and evaluate here on my limits, or I can just keep that and evaluate them all at the end. Either way, it doesn't matter, because the limits are going to be the same, right, for both integrals. So then I have minus the integral from 0 to 1/2 of x of this guy dx. Okay. So what about this guy? Now I'm saved, though. This is not a hard integral to do. This is a u substitution, right? Because if I do u being 1 minus x squared, then du is minus 2x dx. And I even have minus, right? So I've got 1/2 du is minus x dx. So I just decided not to change the limits and just leave them there and then evaluate everything at the end. So that's what I'm going to do. If I make this substitution, the minus, etc., I'm going to end up with 1/2 u to the negative 1/2 du, right? So when I integrate that, it's just u to the 1/2, right? Because the 1/2 cancel. Well, the 1/2 comes from the other one. So x inverse sine of x, this guy, plus u to the 1/2, evaluated whatever, but I'm just going to write the whole thing now. It's going to be x inverse sine x plus u to the 1/2. I'm just going to write it as the square root like this. And now evaluating from 0 to 1/2. Okay. So far, so good? So again, in this case, I didn't have to do integration by parts twice, just because it worked out really nicely, you know, because I ended up with this thing that I could do a u substitution for. So again, it's just all going to depend on the form of what you're integrating. Inverse sine of 1/2 plus, so I'm just evaluating here, right? Or I could do it here. It doesn't matter. It's going to be the same thing, right? So I've got the square root here of 1 minus 1/4, and then I'm subtracting 0 times inverse sine of 0. Let's just do 0 plus square root of 1. Okay, so don't forget to evaluate at 0, even though this guy's 0, this guy's not 0. So I would get the wrong answer. So let's see. Inverse sine of 1/2. No. This one, right? So this be pi over 6. Okay? So I have 1/2 times pi over 6, so I have pi over 12. And this is root 3 over 2 minus 1. I didn't do anything else with that. So plus root 3 over 2 minus 1. And that's my answer. Okay, it's a little bit small down here, but that is what we got.